Okay, so now we're going to take concepts that we're familiar with in the context of translational motion, namely kinetic energy, work, and power, and we're going to transfer those concepts over to rotational motion. So in the context of translational motion, kinetic energy, 1/2 mv squared, is, one way that nature has of storing energy. It's stored in the motion of massive objects. Work, force dot displacement, is energy transfer. So if I do some work, what I'm doing is I'm transferring energy. I'm transferring kinetic energy to this object. And power is the rate at which that transfer happens, which is force dot velocity. Okay, so for a given force, if the velocity is small, the rate of energy transfer is small. But for that same force, if the object is moving quickly, then the rate of energy transfer is larger. Okay, so we have all those ideas in translational motion, and we just transfer them over to translational motion. We just transfer those over to rotational motion. Clearly, I've got this object; it's got some mass, and there's chunks of mass in motion, right? So as this thing is turning, this chunk of mass is in motion. There's a 1/2 mv squared kinetic energy associated with this chunk of mass in motion. There's also a 1/2 mv squared kinetic energy associated with this mass in motion. So objects that are rotating, massive objects that are rotating like this, well, they store kinetic energy, just like in translational motion. And work, force dot displacement, becomes twisting force, or torque dot angular displacement. Okay, and power, instead of force dot velocity, it becomes twisting force, or torque, times the angular velocity. So if the object is spinning slowly, a given torque will only transfer energy at a slow rate, at a low rate. For the same torque applied to an object that's spinning quickly, the rate of energy transfer will be larger, the power will be larger. Okay, so to fix ideas here, what we'll do is we'll start with the simplest possible rigid body that we can construct, which is our elemental rigid body. So we have a point mass, m, which is attached with a massless rigid body, massless rigid rod, to a pivot point. And so then we can have this rigid body rotate about any axis passing through that pivot point. Say we could have an axis passing this way through the pivot point and the mass goes around like this, or we could have the axis passing through that point perpendicular to the board, in which case the mass rotates around in a circle in the board like this. And that's the example that we'll take. Okay, so we'll have the object rotating at this instant of time with some angular velocity omega, and there is the length of the moment arm is equal to r, and at this instant of time we can think of the object as instantaneously moving along the x-axis with some velocity vx, okay, at this instant of time. However, because we've attached our point mass with a massless rigid rod to that pivot point, the trajectory of that mass is not along the x-axis, it's actually tangential to a circle of radius r. So it's actually doing that. Okay, and so that velocity along the x-axis is equal to the tangential velocity of that mass tangential to that circle. So that's v tangential. And then we remember that v tangential, the meters per second velocity of a point on the edge of a rigid body, is equal to the angular velocity omega times r. So that's the angular velocity omega times r. This relationship, remember, comes from the vector relationship, that the tangential velocity vector is the angular velocity vector across r. Okay, and so the angular velocity vector comes out of the board in this case. Remember, you stick your thumb in the direction of the angular velocity vector, and then your fingers curl in the direction of the rotation, the radian at a certain number of radians per second. And the vector r here is the vector which points from the axis, perpendicular vector which points from the axis to the edge to a point on the edge of that rigid body. And this vt here is this actual vector here. And so if you go omega cross r, so this is omega cross r is a vector that's up. Okay, so we have that. And so this tells us that the kinetic energy this mass in motion, like this, is just the same as the kinetic energy of a mass moving with a linear velocity Vx at this instant of time. So that's just 1/2 m Vx squared. Okay, but Vx is the same as Vt, the tangential velocity at that instant of time. The velocity along the x-axis is the same as the tangential velocity along that circular arc. Okay, and so that V tangential is omega times r. That's a squared. So we get an omega squared and an r squared. So we'll write this as 1/2 m r squared omega squared. And then what's this mr squared? Well, mr squared is the moment of inertia. It's the resistance that our elemental rigid body presents to changes in its angular velocity. And so this is just 1/2 moment of inertia times omega squared. Now, this formula, that the kinetic energy of this rigid body is 1/2 I omega squared, we derived this in the case of our elemental rigid body. But in fact, it's true for any rigid body, because any rigid body can be constructed from a whole bunch of these elemental rigid bodies. Okay, so it looks something like this. Here is our sort of generic 3D volume-filling kind of rigid body, and we would like to have this rigid body rotate about some axis, say this axis passing through the body, let's say. Okay, so there's some angular velocity omega. Okay. The vector is, of course, in this direction. That's the omega vector is in that direction. And the body is curling around. It's rotating around in the direction that my fingers curl. Okay? So that's our generic rigid body, rotating with some angular velocity omega at some instant of time. And then we just break that body up into a whole bunch of little pieces. Okay, so here's a piece with mass m1. Here's a piece over here with mass m2. I don't know, here's a piece over here with mass m3, and so on. And then we just write down, well, what's the kinetic energy? Well, the kinetic energy is equal to the kinetic energy of this object. So this is an elemental rigid body. If we take the mass m1 and connect it with a perpendicular, massless rigid rod, okay, of length r1. Okay, so that's perpendicular. So it'll be 1/2 m1 r1 squared times omega squared. Because remember that all of these, all of the masses making up that rigid body are rotating with exactly the same angular velocity, exactly the same number of radians per second. Okay, so if it goes around once in 1 second, then every mass in that body has an angular velocity of 2 pi radians per second. Okay. And then so this here is the kinetic energy of that piece of that rigid body. And then for this piece of the rigid body, maybe this piece is coming out here a little bit. And so the perpendicular distance from that point mass to the axis of rotation is, let's call it r2. So it'll be plus 1/2 m2 r2 squared times omega squared. And then similarly for this guy over here, m3, r3, and so on. And so you see that 1/2 omega squared is common to all of these terms, and what's left over is an m1 r1 squared, the moment of inertia for that mass, for that piece of the rigid body, plus m2 r2 squared, the moment of inertia for that chunk, for that piece of the whole rigid body, and so on. So the sum of all those guys gives the moment of inertia, the total moment of inertia for this whole rigid body for rotation about that particular axis. So this is for that particular axis. Of course, if we take this rigid body and we rotate it about a different axis, like this axis over here, well, then this calculation will be totally different, okay, because you can have the same m's, okay, m1, m2, m3, and so on, but all of the r's will change, and so you'll get a different moment of inertia for rotating about a different axis, okay? And so then this is a general formula. So kinetic energy of a rigid body that's rotating with angular velocity omega is 1/2 I omega squared, where I is the particular moment of inertia for rotation about that particular axis. And you can see, oh yes, well this is completely analogous to kinetic energy in translational motion, which is just 1/2 the mass of the object times the translational speed squared. Okay, so instead of just an inertia and a linear velocity, we have an angular inertia, or a moment of inertia, and an angular velocity squared. Okay, very good. So that's a little bit about kinetic energy of rigid bodies that are rotating. But now what about work? What about transferring kinetic energy to a rotating body? Okay, so let's suppose that we'll just draw a generic picture of our rigid body. So here's a generic rigid body like this, and we are going to imagine that there's a pivot point here, and we can rotate that rigid body, about that fixed pivot point, around any axis that passes through that pivot point. And we'll choose the axis to be perpendicular to the page, and so the object is rotating like this in the plane of the board. Okay, and so let's see. So there's some angular velocity omega. Okay, and now what we want to do is we want to say, okay, in say some small amount of time delta t, this object will rotate. Okay, so it'll rotate through some angle. And so how do we determine that angle? Well, we pick any other point, say P, in the original rigid body here, P. And then as time delta t goes on, this object rotates. And so this point P moves along a circular arc to this point over here. And so point P, we'll choose that point P to be some moment arm or radial distance r from the axis of rotation, perpendicular distance from the axis of rotation. And during that little time delta t, the object changes its angular position by this amount. So this is delta theta, theta final minus theta initial. And this delta theta is thought to be infinitesimal. In fact, we'll write it as infinitesimal. Instead of delta theta, we'll write it in a calculus way as d theta. Okay, d theta is what I really wanted to write. Okay, great. So we got that. And what else have we got? Okay, so now just in terms of the kinematics, so remember that that the angular velocity omega, the instantaneous angular velocity omega, is equal to the rate at which the angular position is changing. So it's d theta dt, and so that's that angular velocity, radians per second at that instant of time that it's rotating at. But now suppose that we apply a twisting force to this, because we're going to we're talking about work here, we're talking about energy transfer. So there's a force dot displacement, a force acting through a displacement. It'll be a twisting force or torque acting through an angular displacement. Okay, so what we're imagining here is we're imagining applying a twisting force torque, okay, in the counterclockwise direction about the same axis that it's rotating about right now. Okay, that's the simplest possible case. And that torque is equal to the moment of inertia of this rigid body for rotation about this axis through that point, and times alpha, the angular acceleration, and that's equal to I. Alpha is d omega dt. So the angular acceleration, if this guy is rotating with some angular velocity already, and we apply a twisting force, well, we're going to increase the angular velocity. So d omega dt, alpha will be, counterclockwise. There'll be some counterclockwise acceleration caused by a counterclockwise torque that we are applying. Okay? So let's see. So these sort of counterclockwise arrows apply not only to the angular velocity omega, radians per second, but also to the angular acceleration, radians per second, caused by a torque, which is also in the same direction. Well, all three of these are vectors, and in this case, they all point out of the board, okay, in the direction of my thumb like this, all right? Great. So now we ask ourselves, well, great, we want to apply a twisting force, a torque, to this object to cause some angular acceleration. So how do we apply that twisting force? Well, the easiest way to do it is to, say, pick a point on the object, say this same point P here, and let's apply a force. Let's grab the object at that point and push that way. So then we're going to have a torque, which is R cross F, which is a twisting force that way, counterclockwise. Okay, and so that's what we're going to do. So this situation, the idea of applying this torque, how do we actually do that? Well, we have, let's just redraw our little picture here. So here's our original rigid body, and then after a small amount of time dt, that object will rotate around to a new angular position. And so we had before, here's this point, the pivot point through which the axis passes, axis of rotation, and then we have a point P over here, located at distance r, perpendicular distance r from the axis of rotation, and P has moved from here to here through some angular displacement delta theta, d theta. I keep writing delta theta today, d theta. Okay, and how we're going to cause that twisting force or that torque is we're going to grab the object at this point and we're going to exert a force in that direction. Okay, and the magnitude of the force, this force is perpendicular to r here, that force that we apply, the magnitude of that force is going to be the torque that we want to apply divided by r. Okay, and that's because that torque got messed up. It's the torque divided by r, and that's because torque is r times f. Torque is r cross f, and if r and f are perpendicular, then the torque is just r times f. So to exert an amount of torque tau that we're talking about, then the required force is torque divided by r. Okay, so we apply that force, that perpendicular distance away from the axis of rotation. That's a twisting force that we're applying. And now the idea of work is force dot displacement. So in this case, the force we figured out already is in that direction of magnitude tau divided by r. And the displacement is the little arc length over here. This is the displacement. So that displacement, which we'll call ds, it's the number of meters along that little circular arc there, is just the radius of the circular arc times d theta. So ds is r d theta. Okay? And so then we can work out, well, what is the amount of energy transferred by this twisting force acting through that small angular displacement d theta? Well, we can apply just the idea. So work is energy transfer. So the energy transfer, well, that energy transfer in linear terms, in translational terms, is the force, the vector dot product of the force and the infinitesimal displacement. So in this case, the force and the displacement are in the same direction. So the dot product is just the magnitude of the force, which is the torque divided by r, times the magnitude of the displacement, ds, which is r d theta. Okay, so you can see that these r's cancel out, which makes sense. Doesn't matter where we grab onto that object, like as long as it's not at r equals 0, pick any point some radial distance r, non-zero radial distance r, away from the axis of rotation, and apply a force in that direction. Okay? And so it doesn't matter it doesn't matter if that r is small or that r is big. If it's a small r, we have to exert a large force. If it's a large r, we only need to exert a small force to get the same torque. Okay, but the result is, of course, independent of r. Okay, and so that's just equal to the torque times d theta. And so what we find is this general result, that the energy transferred, the work done by that twisting force tau through that infinitesimal angular displacement d theta is just the torque times d theta. Okay, and so this result is completely analogous to the idea of in translational motion, we have, say, along the x-axis, instead of along the arc of the circle, along the x-axis, we just have force in the x direction times displacement in the x direction, while that's the energy transferred. Okay, and so this is exactly analogous to the result that we know in translational motion, which is work is the force, say, along one particular axis, Fx times the displacement along that axis. Okay? And so I guess one thing to say here is that this work can be positive or negative. I'm going to run out of room here. Okay, well, let's just do this down here. So this work will be positive if both tau and d theta are positive, or if both tau and d theta are negative. Okay, so positive if the torque and d theta have the same sign. Okay, so that's this kind of situation. So the twisting force is, let's say, counterclockwise. Okay, and d theta is counterclockwise. Okay, so if they're both in the same direction, so that means that as the object is already rotating counterclockwise, so that in a small amount of time dt, the angular displacement will be in the counterclockwise direction, d theta. Okay, and you're applying a twisting force, a torque, in the same direction as well. And so if it's rotating at some small angular velocity, after applying a twisting force in that same direction, the angular velocity will increase, and the work done, or the energy transferred, will be positive. Okay? It'll be negative, the work done, the energy transfer will be negative if the torque and the angular displacement have the opposite sign. Okay, so suppose that the angular displacement, suppose that the object is rotating in the counterclockwise direction, and so d theta is counterclockwise, but we apply a torque in the opposite direction. Okay, so that means it's spinning with some angular velocity, but we're applying a torque in the opposite direction, and so we are slowing down its spin rate, and so omega is going down. So in that case, it looks like this. So that's the d theta, and that's the torque. Okay, and so in that case, the torque times d theta will be negative, and the energy transferred is negative because the kinetic energy has gone down, because we've slowed the thing down, right? So signs are important to pay attention to. Okay, so now remember that this applies, this is a completely general result that applies even if the torque is not constant. Okay, but as long as the displacement is infinitesimal, then this is true. This is sort of the the amount of energy transferred over an infinitesimal torque acting over an infinitesimal displacement. Okay? If we want to figure out the work done or the energy transferred through a finite displacement, then we can do that as well. Let's see. So let me get rid of this here. Okay, so with the board cleared there, let's now extend this to the case of finite angular displacements, the energy transferred during finite displacement. So for finite delta theta, delta theta being theta final minus theta initial, all we do is we just integrate this expression. Okay, so let me see, let's put it down here. So then the work done, let's put it over here. So then the work done is equal to the torque times d theta integrated over a finite angular displacement from theta initial to theta final. Now during that time that the object is rotating through that finite angular displacement, this torque could depend upon theta. So the torque could be changing, and you really have to do an integral like that. And this result is exactly analogous to the case of translational motion, where the work is equal to the instantaneous force. Say, let's say we're moving just along an x-axis. It's fx dx integrated from x initial to x final. So it's completely analogous. But instead of a translational force in the x direction, we have a twisting force about an axis of rotation. And instead of a linear displacement dx, we have an angular displacement d theta. Okay. Now, in the case that in the special case that the torque here is constant, we can pull it outside of the integral. And then we don't have to do a complicated integral, and the result is really easy. And that's why we like to have situations in Phys 121 where the torque is constant. Okay, so for constant torque, and you'll notice that, of course, when we apply a constant torque, then this rigid body will undergo a constant angular acceleration. So we have those simple kinematical formulas that apply for constant angular acceleration. So this is the same thing as constant angular acceleration, alpha. Then we can pull the torque outside of the integral, and then the work done by a constant torque as it acts over a finite displacement from theta initial to theta final, that work is going to be equal to the torque pulled out of the integral times just the integral of d theta from theta initial to theta final. And so that's just adding up all the incremental changes in theta. Well, that's just the total change in theta. That's just delta theta. Okay, so that's the torque, the constant torque, times delta theta. And this result is exactly analogous to the expression we have for constant force. If the force is not constant, we really have to do an integral. And work is not just force times distance. Work is the integral of F dot dr. Okay, along just the x-axis, it's fx dx is the integral that we have to perform. But if the force is constant, we can pull it out of the integral, and the work is just this constant force, fx, times the integral of dx from x initial to x final is delta x, x final minus x initial. So they are exactly analogous. Okay, so that's very good. And so let's give a quick example here. So suppose that we have, this is a constant torque example. Okay, so for constant torque, we'll imagine this sort of example. We'll suppose that we have a rigid body like this, say like a rod like this, and that this rigid body is rotating around an axis perpendicular to the board, passing through the end of the rod, okay? And so the idea here is this object is rotating around and around. At this instant of time, it has some angular velocity, some number of radians per second. There's some kinetic energy associated with all of this mass in motion, okay, initially. And then what we do is we apply a twisting force, a torque, in the same direction as the angular velocity, and so then the angular velocity will increase. So sometime later, after the object has undergone a finite angular displacement from this angle to that angle, okay, some delta theta here, then that constant torque that we have applied will have transferred a certain amount of kinetic energy to that object, to that rotating object, and so it will be rotating faster. So here the angular velocity is small. Apply a twisting force that's constant, the angular velocity is larger. Okay, it's spinning faster. Okay, so let's just look at that example. So we have this rod, okay, which is rotating about its end point around an axis that's perpendicular to the board here. And so what do we want to show? So there's some initial angular velocity, which is small, omega initial, smaller number of radians per second. And then what we do is we apply a twisting force, a torque, which is counterclockwise in the same direction as the angular velocity. And so that torque will act over some finite displacement. Okay, and so this rigid body will rotate from this angle to that angle, angular position, and so there's some finite delta theta here, theta final minus theta initial. And so that torque acting over that finite displacement delta theta is going to transfer kinetic energy to that rotating body, and so its angular velocity will increase. So the angular velocity later is larger than the initial angular velocity. Omega final is bigger than omega initial. Okay, and so then we can just work this out. So the work done by that twisting force acting through that finite angular displacement is the energy transferred. And that's equal to, according to our little formula here, it's the constant torque times the finite angular displacement delta theta. Okay, but then the torque that we are applying, which is from dynamics, we know that torque is equal to the moment of inertia times the angular acceleration. So what causes angular acceleration? Well, a torque. Okay, and so we have torque is I alpha. Okay, and then we multiply by delta theta, and then we say, oh, wait a minute, I recognize this. I recognize alpha times delta theta. Okay, so we remember if we have constant torque, that means we have constant angular acceleration alpha. And for constant angular acceleration, we have this kinematical formula that says omega final squared minus omega initial squared is equal to 2 alpha times delta theta, which is exactly analogous to, in translational motion, v final squared minus v initial squared is twice the acceleration times delta x. Okay, so we just apply that here. Here's an alpha delta theta, and there's an alpha delta theta. And so we just substitute for alpha delta theta there, we substitute 1/2 omega final squared minus omega initial squared. And there's a factor of I in there. So what we find is that the work done turns out then to be equal to 1/2, coming from this 2 here. Work is proportional to I, so times I, times omega final squared minus omega initial squared. Okay, but as we just talked about a few minutes ago, the kinetic energy of this object, of this rotating object, there's mass in motion. Okay, and so the kinetic energy is 1/2 I omega squared. Is it 1/2 mv squared? It's 1/2 I omega squared. And so this is kinetic energy final minus kinetic energy initial. So that's change in the kinetic energy, which is, of course, the amount of energy transferred by that twisting force or torque acting over a finite displacement delta theta. Okay? Very good. Okay, and so we end up with, let me just erase the board here. Okay, and so what we end up with is a generalization of the work kinetic energy theorem and also the conservation of energy principle, which is just a generalization that now includes kinetic energy associated with objects rotating and work done or energy transferred by torques acting through angular displacements. Okay, so the work kinetic energy theorem, the work delta K theorem, doesn't change at all. It looks the same. So it's the total work done is equal to the change in the kinetic energy. The only thing that's different here is that by total work done here, we mean not only the work done by linear forces acting through linear displacements, F dot dr type force works, energy transfers. We're talking about twisting forces or torques acting through angular displacements. Okay, so this includes now the work done by torques, twisting forces through angular displacements, and this change in kinetic energy. So kinetic energy can be stored in translational motion, but it can also be stored in massive objects that are rotating. So we include kinetic energy, changes in kinetic energy associated with changes in angular velocities of rotating bodies. So this includes now change in kinetic energy that's stored in the rotation of objects. So K rotational. Okay, and conservation of energy has the same form. So energy conservation. This is energy transfer. This is energy storage. Okay, and so in an isolated system, the total amount of energy can't change. So the change in the total energy is always 0, and that change can happen because there's changes in kinetic energy. Some objects are increasing their energy of motion, some objects are decreasing it, and so on. Plus there could be change in gravitational field energy, plus change in energy stored in springs, dot, dot, dot. Okay? And so what changes here is nothing except in this change in kinetic energy here, we include also changes in the kinetic energy associated with objects rotating, say at different angular velocities. Okay, very good. And the last thing to mention here, before we go on to an example, a really nice example, is the idea of power. Okay, so rotation, power associated with rotational motion. So remember that P is the symbol we use in physics for power, and that's equal to the rate of energy transfer. Okay, and so we worked out if we are applying a twisting force. I guess it's erased from the board, but if we're applying a twisting force, a torque tau, and the object has an infinitesimal angular displacement d theta, then the energy transferred as the work done is tau times d theta. So then the question becomes, well, that's great. We've transferred some energy to that object, but at what rate? So if we transferred that energy in a small amount of time, it's a high rate of energy transfer. If it took a long time to transfer that amount of energy to the object, it's a low rate of energy transfer. High power, low power. Okay, so power is the amount of energy transferred divided by the time it took that transfer to take place. For a given energy transfer, the smaller the time, the larger the power, the larger the rate of energy transfer. Okay, so if we're applying a twisting force to an object, and it's being displaced through an infinitesimal displacement d theta, then the amount of work done, or the energy transferred, is the torque times d theta, which can be positive, negative, or zero, divided by dt. And then what's d theta dt? Well, that's just the rate of change of the angular position. Well, that's the angular velocity, radians per second. So this is the torque times the angular velocity, omega. Okay, and so we have this general result that power is equal to torque times angular velocity. And this is completely analogous to the idea in translational motion that power is force dot velocity. Okay, so, and if we're just moving along the x-axis, just x-axis instead of something moving around a circle, okay, just x-axis here, then this will just be fx times vx. Okay, and so this fx vx is exactly analogous. Instead of linear force times linear velocity, it's angular force, or torque, times angular velocity, omega. But it's exactly the same concept. Okay, and so what it means in particular is that if we're applying a given twisting force to, say, an object that's rotating slowly, then the rate of energy transfer is small. But as that object picks up rotational speed, angular velocity like this, faster and faster and faster, applying the same torque to a quickly rotating object requires a higher rate of energy transfer. Okay, it's exactly the same as in translational motion, but it's just all rotational. Okay, and so I'll just sort of comment here that, again, this power transfer can be positive or negative. Okay, so you can be transferring kinetic energy to a rotating object, which means, positive, in which case you are increasing the angular velocity and kinetic energy, or you can be transferring negative energy, so really just pulling energy out. And so the energy is decreasing, the kinetic energy is decreasing, the angular velocity is decreasing. So that power can be positive or negative. So it'll be positive if the torque and omega have the same sign, either both positive, say both counterclockwise, or both negative, okay, both clockwise. So this is positive if the torque and the angular velocity have the same sign. Okay, so if we have an object which is rotating, a rigid body which is rotating in the counterclockwise direction already, and we apply a twisting force or a torque in the same counterclockwise direction, then torque and omega will have the same sign, and their product is positive, and that's because we're transferring positive energy to it. We're making it spin faster and faster in the same direction as the original omega. It'll be negative, if tau and omega have opposite sign. Okay, so suppose that we have an object which is rotating counterclockwise. So the angular velocity is counterclockwise like that. But then we apply a twisting force in the opposite direction. It's rotating this way, but we're twisting it this way. Okay, and so in that case, we're opposing the angular velocity and we are reducing the angular velocity. And so we are reducing the kinetic energy, and so we are transferring negative energy to the system or pulling energy out of the system. Okay, and so in that case, this is the angular velocity is counterclockwise and the torque is clockwise, in which case the energy transfer, the power or rate of energy transfer is negative. Okay, so that's just kind of taking these important concepts of kinetic energy, energy stored in the motion of masses like this, but now we're translating it over to rotational motion. These masses are also in motion. So instead of 1/2 mv squared, we have 1/2 I omega squared as kinetic energy, energy stored in the motion of masses. You know, work done is, in terms of translational motion, is force dot displacement. Now in rotational motion, it's twisting force or torque dot finite displacement, or sorry, dot angular displacement. Okay, and so we have this kind of result. And then we talked a little bit here about power, the rate of energy transfer. So again, if we're applying a given twisting force and the angular velocity is small, then the rate of energy transfer is low. But if we apply the same twisting force to a rapidly rotating object, then the rate of energy transfer is larger. Okay, so that's these ideas: kinetic energy, work, and power applied to rotational motion.